Hey everyone, this is a video that I'm using in my AP Calculus AB class. However, I'm putting it online in case it would be helpful to others as well. There is a link to a printable set of guided notes that you can use to go along with this video if you would like. In this section, we are going to be looking at 6 basic derivative rules that everybody is going to need to know as we further our study on derivatives. These are what everybody likes. They're called the shortcuts. We're moving away from doing a derivative using a limit definition, and we are going to start to take a look at all different kinds of shortcuts that you're going to use throughout the rest of your study in calculus whenever you need to take a derivative. Here's the 4 first rules that you need. Now, what I suggest is that you pause the video for a moment so that you can copy all of this down if you are actually taking notes on it. I am going to talk about them briefly, but you might need some extra time. So again, you might want to pause. The first one is one that everybody loves. If you have a function that is a constant function, think about it. It would be a horizontal line. And at this point, we should all know that derivative means slope, right? So the slope of a horizontal line is 0. That means the derivative of a horizontal line is 0. Here's a very quick example. If you had something like y equals 4, then you could identify the derivative. I just chose to use the dy over dx notation for this one as 0. This will work for any constant, and probably one that I should point out, we could put like another little additional example, is pi. If you have pi, which I know we don't often just study the pi constant function. However, I do want you to keep in mind as we continue to study calculus that pi is a constant, right? And so therefore its derivative is 0, or we do need to treat pi like a constant. Okay, next one is the power rule. This is one that if you're in my class, we've already discussed it. Here we're just formally writing it down. The power rule states that if you have x to a power, n is not a variable, n is going to be a numerical power, a number here, then the power rule says that the power comes down in front as your multiplier, and you subtract 1 from the original power to get your new power. Here are a couple simple, here's a simple example. If I have something like x to the 3rd power, then the derivative is 3x squared. Here's one that's maybe not too simple or intuitive. I wonder if I have an orange. Maybe that'll work. Let's see. Because I should probably add something here. Okay, if I have y equals 1 over x, keep in mind that you can use the power rule on that because you could rewrite it as x to the -1 power. And so that's how this derivative has come to be negative x to the -2 power. The -1 comes down as the coefficient, and you subtract 1 from -1 to get your new power of -2. Actually, one other one that I think we should add somewhere in this little example box, because it's important, is any sort of root function can also be derived with the power rule, because a root function, such as the square root of x, can be rewritten as x to a fractional power, right? This one would be the 1/2 power. And so from there, you can again get the derivative using your power rule. The 1/2 would come down in front of the x, and you would subtract 1 from 1/2, which would make a -1/2 new power in this case. Okay, power rule, everybody knows and loves it, right? It's super easy, and it works for a ton of situations. All right, next. Why is this red? It's because I copy and paste stuff, and then I forget to double check it. Whew, crisis averted, except that I'm recording. Here now is in yellow. Okay, here's the next rule. It's one that's forgotten often anyway, but you will probably just do it intuitively for the most part. If you have a function where you have a constant times your function, I should probably note that in here as well, k, a constant. Woo, let's spell constant correctly. There we go. Then the derivative of the function is just going to be k, that constant, times your derivative, if that makes sense. Let me show you a really simple example. Okay, we know that the derivative of x to the 5th, if we just had x to the 5th, I'll write that over here. The derivative of x to the fifth is 5x to the fourth, right? Because of the power rule, we know that. However, if you had 3x to the fifth, 3 being the k in this case, your constant multiple, then what you're going to do is take the derivative of x to the fifth, multiply it with that 3, and that's where the 15x to the fourth is going to come from. Okay, this one will come in handy, especially when we get into other types of functions like trig functions, exponential functions, logarithmic functions. Anytime you have a constant multiple with any of those functions, you just carry it along when you take the derivative of those functions. You don't need to know those ones yet, but soon you will. Okay, so keep in mind this constant multiple rule. And finally, the fourth very simple rule is our sum or difference rule, which just says that if you have a function that is composed of terms that are added or subtracted together, then the derivative will be the sum or difference of those pieces. So a really simple example here, if I have r equals x squared minus 3x plus 7, then the derivative is going to be 2x minus 3. We have some bells happening. Yay! There will probably be more than one bell. I don't know. There might be some announcements as well. I might need to pause this video at some point. All right, let's apply the sum difference rule, and actually all of these rules in example 1, where I think it'll all come together and make sense. Yeah, we're basically going to apply every single one of these rules here. It says find dp over dt if p equals t cubed plus 6t squared minus 5/3 t plus 16. Oh, I feel like I should mention something that's kind of important. Do you know, the bell threw me off. That's why I forgot to say this. Okay, so obviously the derivative of 7 is 0, and so that's why you don't see a third term here, right? But are we okay with, what is the derivative of minus 3x? It is minus 3, right? Derivative is slope. So this is a linear term. You can see the slope in the coefficient of the x. So we just carry that down in our derivative. The x goes away. We're just identifying the slope here. Okay, or also you could think about this as power rule, but it's a little bit of an overkill. This is minus 3x to the first power. The 1 comes down and multiplies with the negative 3, keeping it a negative 3. You would subtract 1 from the power. 1 minus 1 gives you a power of 0, right? And x to the 0 power becomes 1. It's negative 3 times 1. That's probably way more of an explanation than you really need, but I wanted to make sure to note that. We're going to see that again right here. It's very simple. I just feel like sometimes as students are just starting out, they get stuck a little bit right here on a linear term. Okay, so, but not for very long, because again, it's very easy. I'm going to start by identifying my derivative equation with dp over dt, because that's how the directions ask me to identify it. Next, I see a sum and difference of terms. I can take the derivative of each piece separately. As I take that derivative, I'm going to be applying the power rule. The derivative of t cubed is 3t squared. Sometimes power rule with constant multiple rule. In this next one, the 2 comes down and multiplies with the 6, making that a 12. Subtract 1 to get your new power. So 2 minus 1 is a power of 1. We don't need to write that. Here, linear term, the slope of minus 5/3 t is minus 5/3. Just drop the t. And finally, our constant function rule, the derivative of 16 is 0. There's your answer. Woo! The last bit of this page is a little you try section where there's some for you to try. If you would like to try them on your own, pause the video, try them, and then come back to me and I'm going to show you the answers. I'm going to pause as well. I'm going to write the answers out and then I'll show you what I got. All right, I'm back and here are the answers to the you try, the first you try, parts A and B. So check yours, see how you did. And I want you to, don't worry so much about notation. So notice that I labeled this as S prime. Your other option could be like ds over dt, or there are actually other ways to denote a derivative as well. So if we differ in notation, no big deal. For this one, I just decided to switch it up and write it as dy over dx, but you could have written it as y prime. Okay, that doesn't matter. What you need to check for in particular, how to do with number B, or letter B, probably you did okay right here, but do you have a negative 3 power instead of a negative 5? I've made that mistake as well. remember that you have to subtract 1 to get your new power, and negative 4 minus 1 is negative 5. How did you do with the cube root? The cube root of x is the same as x to the 1/3 power. And so to get that derivative, we have a 1/3 x to the negative 2/3 power, because 1/3 minus 1 is negative 2/3. I should probably note before we move on that you could also write your answer to part B like this: negative 48 over x to the 5th power plus 1/3 times x to the 2/3 power. You could change this to cube root of x squared if you would like, but there's not a ton of circumstances where you would have to rewrite it in that form, so that's an optional step. All right, I just lost where I was. The first 4 derivative rules are the most basic derivative rules, and they're all right. At least they're pretty intuitive, but they're not super fun. What we're going to now do is talk about 2 other rules that I just think are a ton of fun. All right, before we get to something called the product rule, a question to consider. Is the derivative of a product of 2 functions the product of their derivatives? And here's what I mean by that question. Take a look at the example. For example, what is the derivative of x times x? Okay, so what I'm asking you here is, if we have 2 functions that are being multiplied, can we assume that we can just take the derivative of each piece separately and multiply those derivatives together? Would that work? Okay, so let's pose it as a question like this. Can we do this? The derivative of x times x, we could leave it as this product, and we could say is equal to the derivative of the first x times the derivative of the second x. The derivative of x is 1, right? Because the slope of x is 1. So we have a derivative of 1 here, we have a derivative of 1 here, we multiply them, and we get an overall answer of 1. Does that work? Does that make sense? Think about what x times x is as a function. It's x squared, right? Is the derivative of x squared equal to 1? No. No! I used to have a student for many years, actually. I had him in 8th grade, 9th grade, and 10th grade math classes. And when I would ask a question where he knew the answer was no, he would say, no, like that. And he just made the class so fun when he did that. All right. Anyway, no, obviously this doesn't work, right? Because we know that the derivative of x times x is the derivative of x squared. And we know that that derivative is 2x. This does not work. No. All right, are you getting the idea? No, you can't do it. So what we need to talk about now is something called the product rule for derivatives. And we're going to apply this rule many, many times this year. So we have to get used to it. Okay, this is like you have any 2 functions that are multiplied together. And for a lot of the initial functions that we look at, like x times x, you could say, well, couldn't I just simplify it and, combine them and make it something like x squared, and then I don't have to know this rule? Yes, for simple functions you can, for simple polynomial functions. However, as we move on, we're going to work with all different types of functions. You could see a product that is like x times sine of x. How are you going to combine that? You're not. You can't. So you're going to need the product rule in that case. So we talk about it here, we talk about it with simple examples, and then you're going to use it again and again and again as we see all different types of examples of different functions where it'll be used. All right, so here is what the product rule says. This is something that students are not fond of. Sometimes we use the letters U and V in calculus. And I know that that's not fun because when you are writing U and V, sometimes they look similar, right? And they're also just weird letters, but it's out there, we use it, and so we're just going to have to deal with it. The product rule says, if U and V are differentiable functions of x, then the derivative of U times V, that's what you're looking at right here, what it's equal to, okay, this is a little bit crazy, it's equal to the U function, this just means U, times the derivative of the V function, plus the V function times the derivative of the u function. That's what your product rule says. Okay, now before we apply it to example 2, let's go back to this example of x times x and see how it works. I'm just going to draw like a little thing here. Okay, so if I have, x times x, and I'm taking the derivative of it, what I can do is use the product rule, which says take the first function as it is. You don't change it. And you multiply that by the derivative of the second function. The derivative of the second function is the derivative of x, which is 1. So we have an x times 1. Plus, it's always plus. Product rule always has a plus in it. The derivative of the second function, gosh, sorry, I'm messing it up. The second function as it is, not the derivative of it, just the second function, times the derivative of the first function, which is another 1. If you think about that, x times 1 is just x times 1 is just x, and x plus x simplifies to 2x. That works to get us what we know the answer should be for the derivative of x times x, or simplified, the derivative of x squared. All right, that may sound confusing. Let's do another example. Find f prime of x if f of x is x squared plus 1 times x cubed plus 3. Okay, again, this is another example where you could multiply these binomials together. You could simplify into one polynomial function and then take the derivative of that. Or you could leave it as a product, and I actually think it's simpler once you know the rule to leave it as a product and just take the derivative using what is called the product rule. The product rule says use your first function unchanged times the derivative of the second function. The derivative of x cubed plus 3 is just 3x squared, right? Because the derivative of 3 is 0. Plus, we're up here, always plus, the second function times the derivative of the first function. Derivative of x squared plus 1 is 2x. Because again, the 1 derivative goes to 0. And that's it. That's your answer. You don't have to, it looks a mess, right? It could definitely be written in a simpler form, but it is what it is. All right, finally, I want to tell you a little saying that I've been using in my classes for years to remind students of this little product rule, what it actually says. I can't take credit for it. One day, it was my first year of teaching calculus. One day, a student looked at it, and he just came up with this little saying off the top of his head. He said, okay, if we're taking the derivative of a product of two functions. He called them function number 1 and function number 2. Okay, 1 and 2 don't stand for just the numbers 1 and 2. This is a function times another function. He said what it is 1 d2. That means first times the derivative of the second plus 2 d1. Second times the derivative of the first. And if you say it quickly, 1 d2 plus 2 d1 has a ring to it, right? And it makes sense. 1 d2 plus 2 d1. You might not appreciate this little saying right now, but I promise you, when I start to say it over and over and over again this year, you are going to appreciate it. Okay. This is a you try. If you want to pause the video and try it on your own and then come back to me and see the answers, you can. But I am going to go over this with you all together. Okay. We have another product of functions here. Y equals 5x squared times 2x. It would be pretty easy to simplify this one. And that's what part A asks you to do. Simplify the function, then find the derivative of y. Okay. So simplify the function, meaning let's multiply this through. 5 times 2 is 10. X squared times x is x to the third. Easy simplification, right? Then find the derivative of it. Y prime is 30x squared. Ta-da! Pretty easy. Okay, but part B and C are trying to show you that if you did not simplify and you just take the derivative of this function using the product rule, you will get the same answer. Watch this. I'm going to go straight from this y to y prime using the 1d2 plus 2d1 product rule. This is the 1, this is the 2. Y prime is 1 d2, the derivative of 2x is just 2, plus 2 d1, the derivative of 5x squared is 10x. Now, in part C, did we get the same answer here that we got here? Well, if we simplify, we will, right? 5x squared times 2 is 10x squared. 2x times 10x is 20x squared. And that does become 30x squared. So yes, we got the same answer. Again, would it be easier to simplify this function and then take the derivative of y in this case? Yes, and you can absolutely do that when you're problem solving for yourself. However, there will be times that simplifying is not possible, and so we do need to understand that this product rule is a thing that you're going to use a lot. I won't let you forget it, don't worry. Finally, listen to this. Don't look at that yet. Don't look at it. Okay. If the derivative of a product of two functions is not as simple as derivative times derivative, then do you agree that probably the derivative of a quotient of two functions is not going to be as simple as derivative divided by derivative? No. Here's the last rule that we're going to talk about in this section. It is called the quotient rule. It looks scary, I know. Write it down, pause, do what you need to do to get it on your paper. If you're taking notes, if you're one of my students, you better be taking notes. And then we'll talk about it, okay? So what we have are u and v again, and u and v are just standing in for functions. Any two functions that in this case we are dividing, okay? And notice that it does have the stipulation here that v cannot equal 0 because the v is in the denominator. This rule, or this little formula, is how you find the derivative of that combination, okay? I know, it just looks so bad. Let's talk it through, and then I'm going to give you something that it'll help you never, ever, ever forget it, okay? Ready? Here we go. This says if you are taking the derivative of a function divided by a function, what you do is you take the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. And I know, like, if you're writing this, if you're listening to me, you're probably like, no, I am never going to remember that. But yes, you are. You're actually probably never going to forget it, because here's what we do. I'm going to tell you my little saying. I can't take credit for this one either, but I can't remember where I got it from. And I did add some pizzazz to it, so I'm going to take a little bit of credit. What we're doing is we're taking the derivative of a fraction that we're going to call the numerator the high. This should be H-I-G-H, but I like to just spell high like that. And the denominator we'll call low. Okay, and ready? Here's the little saying. The formula is low d high minus high d low all over a low. Woo! Ready? Here it goes again. Low d high minus high d low all over a low. That is how you are going to remember the quotient rule. I promise you, it will stick with you and you will never, ever, ever forget it. I should ask like students from 10 years ago, do you still remember the quotient rule? Okay, so what it says is you have the lower function times the derivative of the higher function minus the higher function times the derivative of the lower function, all divided by the lower function squared, but we don't like to say low squared, only psychos say low squared. We say a low because it makes the saying nice and smooth. Let's do it right here. Differentiate the function f of x equals x squared minus 1 over x squared plus 1. Okay, listen. You definitely cannot just do derivative over derivative, okay? The derivative of this is not 2x over 2x, which would cancel to 1, except at x equals 0. No, that's not going to work, okay? Quotient rule here, quotient rule. Ready? This is low, this is high. It is low d high. The derivative of x squared minus 1 is 2x. This is the derivative of x squared minus 1. Minus, it's always minus, high d low, all over a low low. Square the denominator. That's your low low. Okay? Sometimes students, the only thing that they do with the saying that will mess them up is they'll start with high d low, then say low d high. No, you don't start high, go low, right? You're starting with low level calculus and we're working our way up. So we start low d high minus high d low over a low low. Now, sometimes I will tell you, you don't have to simplify, just leave it like that because we need to move on to more important things. However, for this example, let's just go ahead and simplify because this does sort of look a mess and it will simplify kind of nicely. So we're going to distribute the 2x here. We're going to distribute the 2x here and the negative, and we'll see what happens. So I have 2x cubed plus 2x minus 2x cubed plus 2x. That's a minus, but that's another minus. All over low, low. I almost never simplify the low, low. Don't expand that. It's not really simplifying, right? All right, 2x minus 2x is 0. Combine your like terms in the numerator and look at this nice derivative answer. 4x divided by x squared plus 1 quantity squared. There's your answer to the derivative using the quotient rule. Okay, finally, for example 4, we see a quotient again. So we are going to review one more time how to take a derivative using the quotient rule. But then because we only have one term in the denominator this time, I will show you another way that you can differentiate. It involves sort of like what we did with the simplifying thing in that last try. We can simplify this one and then do a derivative that would not need quotient rule, but that's going to be the part B part. What I want us to do here first in part A is just let's do a y prime using low d high minus high d low all over a low low. Ready? Low d high is also 2x. This is low d high minus high d low is just 2 all over a low low. Be careful, put that 2x in parentheses and square it because that's going to become 4x squared. 2x times 2x is 4x squared, right? So you need those parentheses around the 2x to show that the 2 is also being squared. All right, simplifying a little bit, we get 4x minus 2x squared minus 6. Again, distribute the negative as well. And again, in the denominator, we have 4x squared. Did I do something wrong there? That feels wrong. This is like, maybe I should look at my key. Yep. I was like, something doesn't feel right there. Do you see what it is? Are you yelling at me right now? That should be squared. Okay. Simplified further, we get 2x squared minus 6 over 4x squared. Because we can combine these like terms now that they're like terms. All right, so there's our answer to the derivative of this function using the quotient rule. But the last thing that we're going to do now for part B is we are going to simplify this function and then take the derivative without having to use the quotient rule. Now again, we can do this here because we have a quotient here, but it only has one term in the denominator. And so we could split the terms in the numerator with that common denominator term, like that, and rewrite as just coefficients with x's and powers. Okay, So that's why it says using the power rule. So I'm still rewriting here. Notice the notation, it's important. I'm not using y prime yet. I'm using just y because I'm just writing simplified forms of my original function. X squared divided by x is x. We have this 2 in the denominator that we can pull out as a coefficient of a half. So we have 1/2 x for the first term. 3 over 2x could be rewritten as the coefficient 3/2 times x to the -1 power. Remember, if you just have a plain x in the denominator, you can bring that out with a -1 power. And now we're ready to take the derivative of this, so y prime, using just our simpler rules. The derivative of 1/2 x is just a half. The derivative here is -3/2 x to the -2 power. Now, believe it or not, this derivative expression and this derivative expression are the same thing. If you divide these two terms in the numerator by 4x squared, you would end up with that. They're the same thing. They're just in different forms. Okay? We're going to end the first video here because I didn't want to make these videos too long. Now, the notes for this section are not done. The other part that we need to do is a little extras part where we take all of the rules that we have just discussed and we apply them to different problem-solving scenarios. That'll be in a part 2 video that'll come out soon. Okay, bye.